12.2. A couple more examples.
Can you say under the plane?
Formed by the plane in the first octave. You could, yeah, it's the same as under the plane. Bounded by the plane and the coordinate axis, you could say that.
Okay.
So do we see what region we want to find? Area. Okay, what would the graph of this tetrahedron look like?
X-intercept at 3, y-intercept at 3, and see it's 6.
So that's the tetrahedron, right? So the YZ plane is one face, the XZ plane is one face, the XY plane is one face, and then this, the plane that slants over like this, that's the fourth face. I want to find the volume of that. How do I find the volume of this?
So the region is the triangle.
The region is the triangle. We can make it in the XY plane. Which, by the way, in general, there's nothing special about the XY plane. I could have made it in the YZ plane or the XZ plane. But it's usually nicer, especially if you can solve for Z readily. Right, so here you can say, and so once you have a function of x and y, what you're going to want to do is you're going to want to integrate that with respect to dx, dy, or dy, dx. Right? So now the volume is just going to be equal to the double integral over r. Let's not call it r, call it d. Of the plane. So how do we set up the limits?
I guess you could have x from 0 to 3.
Y equal 3 minus x.
So on the xy plane, if these guys are hitting 3, that's the region D. Right. So this is the line y equals 3 minus x. Right? And so you can let x go between 0 and 3 if you'd like. And then y would go between what and what?
0.
0 and 3 minus x, because it goes from the bottom function to the top function. So this is just 0 to 3, 0 to 3 minus x. Constant's always on the outside, which means I need my x on the outside and my y on the inside. 6 minus 2x minus 2y. And from there, now we just integrate. And plug in 3 minus x for the y. So it's 6 times the y, 3 6 is 18, minus 6x, and minus 2x times this gives me minus 6x. Minus 2x times x gives me positive 2x squared. And then I plug in the 3 minus x into the y, so we have that. So this guy is minus 12x. So now we can integrate that. This is 18x minus 6x squared plus 2/3 x cubed minus 3 minus x cubed over 3 plus between 0 and 3. Plug in 3's everywhere, so 18 times 3 is 6 times 9 plus 2 times 9 plus 0 minus, now I plug in 0, I get 9. So this is really, these are the same. And so I just have 9. Okay, change the order of integration. This was a bonus problem on the last quiz, on the last exam. Notice here that you actually couldn't do it if you didn't change the order, right? Because you can't integrate e to the y squared with respect to y. So that's going to be bad. So it's better to integrate here with respect to x. So that's what we're going to do. And first thing I'd probably do is draw the region. What does this region look like? Described by inequalities.
Between 0 is less than y is less than 2. Oh, I'm sorry. 0 is less than x is less than 2.
And the y? X up to 2, right? So we're looking at the function x, which is just that. The function y equals 2, it's a horizontal function like that. Of course, since this is y equals x and that's 2, then this will also be 2. So we know that x is going from 0 to 2. Now, which one of these regions do I shade?
Left.
This one?
Yes.
Y.
This x is on the bottom.
Because this is the bottom curve, and that's the top curve, right? So 2 should be on top of your shaded region, and x should be on the bottom of your shaded region. So we know that's the region we want to do, right? So now we're actually going to switch the roles. We want to describe y to go between constants and the x to go between functions. So describe the exact same region, but now in the reverse way. What are the constants for the y?
0 to 2,
So again, 0 to 2. What about for the x, the functions?
y to 2.
0 to y, right? Because if you look on the shaded region, what's the function on the left? This, which is x equals 0. The function on the right is this, which is x equals y. So it goes from 0 to y, because it's always left to right. So this means this integral 0 to 2, x up to 2, of 2 e to the y squared, dy dx is actually equal to, I can do 0 to 2, 0 to y of 2 e to the y squared dx dy. How do I integrate that? Integral of this with respect to x. Now if I plug in y for the x, I would get 2y e to the y squared. Plug in 0 for x, then everything dies, so it's just that. And so this is just e to the y squared between 0 and 2. Which is e to the 4 minus 1. Right? We're technically to do a u substitution, u equals y squared du d2y. So a lot of times switching the order might be the way to go, and of course they're not always going to tell you that you have to switch the order. Sometimes you just have to figure it out, because if you're given this, you can't integrate with respect to y. So your only shot at doing this one is to try to switch the order, which is, this is how you do it. So you draw the region, you describe it just by reading off the limits here. And then what you want to do is you want to switch the roles. Whoever was between constants before is now between functions. Whoever was between functions before is now between constants. But you're describing exactly the same region, right? So you're not changing the value of the integral. You're just changing the way you're expressing it. So that's a neat little trick. I don't know if I wrote this in general. In general, we can think of the volume similar to how we have area formulas in Calc 2, where we know it's the integral of the top function minus bottom function. There's a similar thing here. The volume in general is top surface minus bottom surface. So that should be something you're always thinking about. Notice here we were employing that, but your bottom surface was z equals 0. So if you subtract 0, it doesn't really matter, right? So especially in 12.1, they were always considering regions above the xy plane, which is 0. So you never really saw this, but in general, it's always there. So that's something you should take note of. So in Calc 2, we could actually split integrals over a subinterval, just reminding you of what that means. So if I had like A, B, C, then I have a random function going here. Then it's actually true that the integral of A up to C of f of x dx is equal to, you can actually split it across subintervals, right? You can go A up to B of f of x dx plus, then you go from b up to c of f of x dx. We can do a similar thing in 3D just to let you know it does work. Except now we're talking about regions. So these are just some familiar properties that actually generalize. It actually generalizes beyond double integrals as well. Double integrals. Reverse of regions. So within the xy plane, you have a region which you call D, or you can split into D1 and D2. Take the double integral over d of f of x, y, dA. It's exactly the same as taking the double integral over d1 of f of x, y, plus the double integral over d2 of f of x, y. Right, so we can actually split over regions just the same way as we can split over intervals. And you can prove that using the Riemann sum definition, but we won't do this. Just know that you're doing that and do that. Another property that we'll use all the time . Area of a region D is actually equal to the double integral over D of the function 1. Always. Right? You want to figure out the area of a region, double integrate the function 1, that will give you the area of the region. Does anyone see why that works?
Yes. Because you'd get the function themselves. Like,
Yeah?
I mean, it's not necessarily the function 1, it's the differential dA. So because you're integrating that with the bounds of dA, you're just going to get the whole area.
Yeah, you could think of it that way. It's like sort of like a fundamental theorem of calculus thing going on. You're integrating a derivative, like the differential. You can do it that, but you can actually also think of it as a function. Notice that if you have
so the bounds of the region are the
some
functions.
random thing, if you have like anything that's cylindrical where you just have the base is uniformly projected, then the volume for this is just the area of the base times the height, right? Right? And here, I just set the height equals 1. Right? That's my function is 1, right? So if I find the volume of that, the volume is actually numerically equivalent to the height in terms of magnitude, right? So you also get it that way. So that's actually something. So it's going to save us a lot of work. So later on, you're going to see where we're going to be setting up these integrals, and they're going to have limits that probably look sort of complicated, but not really. But we're going to be able to just say the answer right away because we know it's just describing an area of a region that we already know how to find. So
Wait, I don't get what's unique about having a 1 over there. Is that a 1?
yes,
Function?
that's the function 1. It guarantees that the volume is equal to the area. If your height is 1, then your volume is equal to the area.
Yeah. Okay.
Right, so that's the thing. So if you see something like that one, what's the answer?
4 times 3 is 12.
12. right? Why is that? Because this guy here is describing a region of a 1 by 3 region. It's just a rectangle, right? The 4 I can factor out. This guy gives me the area, which I know is just 1 by 3 times the 4, which is the 12. Like I didn't have to go, oh, x and then plug fundamental theorem and calculus, then integrate, get the y, and then fundamental theorem and calculus again, right? You can sort of see shortcuts with that. I mean, it's going to look nicer when we get to some further chapters. Anything else I need to mention? Okay, this is an example of finding the area. Another FYI, I don't know how often we're going to use this property, but it works. Probably need it in the homework. So probably it helps you to bound things every now and then. Might come in handy. Okay, how do I find this area?
Well, it's a triangle, and if you wanted to use integrals, do you want to use that?
I want to use integrals.
Okay, so it would be 0 to integral 0 to x dy dx.
So we actually have y equals x equals 2, the x-axis. So this is our region here. So this would be y equals x. And so your area would be the double integral.
0 to 2, 0 to x dy dx.
Right, times the function 1 dy dx, which is going to give you what? It's 0 to 2. You integrate this with respect to y, you just get y between 0 and x dx, which that's just the integral from 0 to 2 of x dx, which is just x squared over 2 between 0 and 2, which is 2, right? Now, if this is, what would be the y value of this intersection? Okay, so what's the area of the triangle by geometry, right? Half base times height, we also get 2. Just an illustration. Okay, let's get to something more exciting now. 4.3. guys all remember polar coordinates from calc 2?
Oh, sure.
I don't know if it's...
Of course we do.
There's an R somewhere.
Well,
What? There's an R somewhere.
I thought those were 5.
There is an R somewhere.
And the theta.
Which they prove. So, I actually want to review it. This one too.
Yeah. Right?
So let's say if f is continuous, says f of x, y is continuous. On the polar region. Here's the formula. It's a very important formula. It's pretty much how you change the polar coordinates. Notice that your dA, right, so in polar coordinates our variables are r and theta, right? And do we... So this is where we try to locate a point based on a distance from the origin, which we call r, and an angle theta measured with the positive x-axis, right? Where here we can actually show that r squared is equal to x squared plus y squared. This follows by Pythagoras' theorem or the Pythagorean identities, however you want to define it. So x is equal to r cosine theta. Y is equal to r sine theta. So that was polar coordinates. And we can basically derive that the differential area. Now, when I say a region is polar, what do we call a polar region?
It's circular?
It's 20 tons aside, one that you can describe and transform.
It's cold.
Yeah. Now, typically, it's mostly beneficial if we're describing regions over part of a circle, because that's how the thing was developed, to really measure circles. There's a region that you can describe by measuring an angle, right? So let's say you have some angle here, theta 1. And then you have another angle going all the way up here, theta 2. There are two functions, right? Can be doing whatever they're doing. So I can call this function g1, or, well, based on that I call it g2 or g1. So anything you can describe in this way as something spanning an angle where you have an inner function and an outer function, you call it a polar region. The most convenient polar region to use polar coordinates are on our circles or parts of circles. Right? So examples of regions that you'd use polar coordinates for, like full circle, or maybe a part of a circle, a segment, maybe like an annulus. Maybe even part of an annulus. All right, so anything sort of this form, most of the time it's actually going to be easier to set up the integral in that way using that formula than it would be to set it up in the rectangular formula. And we're going to talk about why. It's because here you're describing the function that describes the circle. It's just that it's this radical with a sum under it. It's very inconvenient to use. Where here you can actually get rid of the sum under the radical by employing that guy. Right? So if you look at the circle x squared plus y squared equals 1. If we want to do it the old way, we'd have to solve for y. Y is the radical of 1 minus x squared. And you're going to have just 1 minus x squared in your limits. It's going to be really ugly and nasty to deal with. However, x squared plus y squared is r squared. So I can just replace that with a single variable. No radicals, no sum. It's just a lot nicer to deal with this, this transformation. So, like, just as you would see normally, your x, wherever you see x in your original function, replace it with r cosine theta. Wherever you see y, replace it with r sine theta. Your dA is replaced with d theta, and they proved in the book why this works. They found the delta A and they described it in terms of areas. We're going to skip that. Yeah, that's it. Yes?
And so I assume you can change the order of integration and integrate the thetas first, but then the r's.
Typically, you're not going to want to do that.
Okay.
Even if you could in theory, it's usually way too much trouble. And
Okay.
it's the kind of thing where when you set it up this way, it just works.
Okay.
Usually. It's not something you're going to want to switch integrals for usually. I mean, not at anyone we're going to look at anyway. Right? So if you're over a circular region or part of a circular region, polar coordinates is what you're going to want to think about. Okay, so let's actually do some examples. It looks confusing now, but you should know this formula. And don't forget that R. Right? Very important to have that R there.
Why is that there?
It's the change in area. So it's like if you're looking up this polar region here, and you want to find the change in area, you sort of find the formula that gives you you sort of think of it like, right, you take a very small slice, right, where you just, this is sort of like circular, right, and you find the area of the whole thing minus the area of the inner thing. When you simplify everything all out, let's say the area of this whole thing is A2, and the area of this inner piece is A1. It turns out that A2, your delta A, which is going to be A2 minus A1, is going to be equal to R delta theta delta R. if you actually apply like lengths to all these things and actually work out the formulas, you'll get that, right, when you find the change in area. Right? So it's a little bit of arithmetic. They do it in your book. I don't really see a point in showing it, because you're never going to have to derive it. You derive it once in your life, and then you never do it again. You just know that every time you're switching to polar, you just put an R there. But it comes from that fact, right? They're just looking at the change in area between the two functions, right? Which is what the dA is in the Riemann sum. Evaluate. Rectangular is what we've been doing. In 12.1 and 12.2, how we set up the integrals is called rectangular coordinates. You just make a note of that. Rectangular coordinates. Refers to x, y, z. Alright, so these might be words they throw at you. They might say, use rectangular coordinates. It means just the old way that we've been doing up to now. Or use polar coordinates, means doing that. Right? And later on we're going to learn other coordinate systems as well. But so far we can do that.
Would you usually specify, or would you just give the function and you use that?
Typically you will decide, so I wouldn't force you. In the case where they force you, it'll be a question like this. They'll say, set it up in these two ways, evaluate one of them, right? So that's a possible question that you can ask. Set this up in polar coordinates and rectangular coordinates and evaluate either one. Now, of course, either one you pick, you should get the same answer, but it's up to you to set it up correctly and then know how to do one of them.
The only difference is that one would be easier than the other.
Yeah, in general. Okay, how do we evaluate this integral? Let's set up in rectangular first, since I think we should know how to do that. D is this disk, right, of radius 1. Now, if I were to set that up with rectangular coordinates, how would it look?
I guess you'd have to split it into two regions.
Right, because it's not a function as it's written, right? Because it doesn't pass the vertical line test. And so you're going to split it into two regions. You probably split it out. The natural way would be to split it along the top half of the circle, which you can write the equation to be what? Radical of 1 minus x squared. Then the bottom part you'd write as negative 1 minus x squared. So in other words, you can say this goes from the minus 1 minus x squared up to the positive 1 minus x squared. Your x would go, where are the limits on the x? Negative 1 to 1. In other words, the integral over d of x squared plus y squared dA could be written as minus 1 up to 1 minus radical 1 minus x squared of positive radical 1 minus x squared of x squared plus y squared dy dx. Right? Now imagine trying to evaluate that, right? So you'd integrate this with respect to y.
Oh yeah.
It's going to be nasty, right? You're going to get x squared y, you're going to plug this into there, then you're going to have to do a trig substitution, right? This guy, you'd have to do a trig substitution again. It's going to
Could
be
you do one
really-
half of that and double it?
In this case, you could, yes. But it's still going to be annoying. You're still going to have to use trig
Right.
So the trig
minus
substitutions
1
are
minus
based
x
on
squared.
polar.
Yeah, this is equal to, you can actually multiply it by 4 and then go from 0 to 1, or 0 to the radical of 1 minus x squared, blah, 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 dy dx. You could do that, but it's not going to save you from doing the trig sub,
Okay.
right? You're still going to have to plug in that huge radical mess, right? It's going to be really messy. Let's try to do it using polar coordinates. So what does polar coordinates say? Place all the x's with r cosine theta, all the y's with r sine theta, replace dA with r dr d theta, then describe the region in terms of a distance from the origin and an angle.
But if you have x squared plus y squared, that's r squared.
That is correct. So, let's look at the region D. Let's describe this region. I mean, we did this sort of on day 1, when I was seeing how much you guys remember. Like, if you wanted to describe this in terms of polar, like r and theta,
R is between 0 and 2pi.
right, remember r is the distance from the origin, right? So you're covering all points from 0 away from the origin, all the way out to 1 away from the origin. So r goes from 0 to 1.
There's 0 to 2pi.
Theta, you're covering all 4 quadrants, right? So it's 0 to 2 pi.
That's it.
That's it. And so now, if you have this guy, you look at this, now what are you going to have? X squared plus y squared is just r squared. The dA becomes r dr d theta. My theta is going from 0 to 2 pi. My r is going from 0 to 1. So really at the end of the day, I just have to do this integral. Which is a lot easier than doing a trig substitution on a really nasty radical. Right? This is easy. We can do with this. Alright, so this is 0 to 2 pi. 0 with respect to r, you get r to the 4th over 4 between 0 and 1, d theta. And you get 1 over 4 times 2 pi. It takes 3 steps. If we wanted to do that directly, it would have been a real mess. Right? That's sort of the power of polar coordinates, that it allows you to do circular regions a lot easier, right? As long as you remember your polar coordinates and how to describe a region in terms of a radius and an angle.
Would it ever make sense to use polar coordinates for a non-circular region?
You'd have to have a good reason for it. Like if you see a bunch of x squares plus y squares all over the place, that might help, even though the region is not particularly circular. But that would take a little bit of work on your part. Whenever your region is non-circular, you won't have constants here. Your r would be described by some functions of theta in general. So,
Have put the theta inside. Have put the theta inside.
yeah.
You mean?
So we'll probably do a couple of things like that, but or do I want to do it now? So that could be a question that you get in Calc 2, right? Anyone remember how to find the area inside a curve? This, by the way, is is the guy that looks like this.
Oh,
All right. How do you find the area of it? In Calc 2, what would you have done? Take a half r squared d theta, right? And you take the limits of t theta goes from 0 to 2 pi or something, right? But in the Calc 3 way, how do we know how we find area?
1.
Double integrate the region 1. Now here, your r, this is measured from the origin out to the curve, right? And that curve is actually described in terms of a function. So here, I can describe my d as r goes between 0 and 2 minus 2 sine, right? And my theta goes from 0 to 2 pi, because I'm covering all 4 quadrants. This means that my area is equal to 0 to 2 pi, 0 to 2 minus 2 sine theta of 1. What's your dA?
thanks.
R,
R dr d theta. Do not forget that R, right? So just because it's a 1 here, the dA becomes R dr d theta. You're going to have that R there. So now when you integrate that, what do you have?
R squared over 2.
1/2 r squared and look, that's the old Calc 2 formula, right? If you actually plug in, this would be 1/2 r squared d theta, right? You get back the Calc 2 formula. So the Calc 2 seal would have picked up here, but this was what was happening in the background back in Calc 2 that they were telling you about. And so how do I actually integrate that? See if you guys remember.
4 theta.
Huh?
4 theta.
How do you integrate that?
Would you expand it?
You'd expand it first, and we get what?
Well, the first term would be 4.
Minus 4 sine squared theta minus
8 sine theta
6
minus,
4
well,
sine.
plus 4 sine squared theta d theta.
And then rewrite sine squared theta
Correct.
As what?
as 1/2 times cosine. Or 1/2, it's either 1/2 plus cosine 2 theta.
It's
Minus.
1/2 times 1 minus cosine 2 theta over 2, right? But then the half would kill this. I get 2 here. So it's 1 minus cosine 2 theta d theta. Remember that if you integrate sine or cosine over 0 to 2 pi, they actually give you 0, so you can actually ignore that part. And so now that's what you have to do. So this is just 1/2 times 0 to 2 pi times, this would be 6 minus 2 cosine 2 theta d theta. Theta. What's the integral of this?
Negative sine 2 theta.
Right, times the negative, so you get a plus 2 sine 2 theta to 0 to 2 pi. Either of these will make the sign 0, so you just ignore that. This is 2 pi times 6 times 2 pi.
Is theta usually from, is it always the case that we'll get theta from 0 to 2 pi?
Nope.
Oh, right, because if it's 3/4 of a second.
It depends on the region that it's describing, right? So it's not always going to be a full circle. For example, if they ask about something in the first octant, then It's not 0 to 2 pi.
0 to pi.
It's 0 to pi over 2. Okay, so another example. Yeah?
Why do you have a slot before the 70?
No, that was a minus. It's still 0 anyway, so the answer doesn't change. Find the volume of the solid. Bounded by z equals 0 and the parabola, right? Z equals 9 minus x squared minus y squared. Inside. Can you draw the object that I want you to find the volume of?
It's an upside down paraboloid.
A bell.
Can you tell me the equation of the curve in the xy plane?
It's a circle.
What's the equation? This is their surface z equals 9 minus x squared minus y squared. To find what it looks like in the xy plane, you just plug in z equals 0, right? And then you can rewrite the curve in terms of x and y. So here's this parabola coming down. It intersects the xy plane on this circle, right? Which means my region, D, is a circle. So I can call that D. Right? So now D, I can describe it as r and theta. Yes?
I have a question. Isn't D smaller than the parabola? Because the radius of D is 2.
Where is that? No, you're looking at B right here.
Oh, okay. Yeah.
Yeah, that's a whole different thing. Okay, so this is our region. I want to find the volume. How do I describe this region? R goes from what to what?
0 to 3.
Theta goes from what to what?
0 to 4.
So the volume is equal to, remember it's the double integral of the top surface minus the bottom surface. So 0 to 2 pi, 0 to 3. What's the top surface?
9 minus x squared minus y squared.
9 minus x squared minus y squared, but I'm switching to polar coordinates, so what does it look like? 9 minus r squared is the top function, right? Minus What's the bottom function?
R squared.
Z equals 0.
0.
Oh,
Right? So it's the bottom plane. So it's just minus 0. Your dA becomes R dr d theta. So the volume is actually equal to 0 to 2 pi, 0 to 3 of 9r minus r cubed dr d theta. Which is just going to be 2 pi times 9 over 2 r squared minus r to the 4th over 4 between 0 and 3. So if I plug in 3 here, I would get what? That's 81. 81 over 2 minus 3 to the 4th is 81 over 4, which is just 81 over 4 times 2, so it's 81 pi over 2. How would the second region look? So it starts out pretty similar. It's 9 minus x squared minus y squared.
and then there's a cylinder.
All right, so this goes up to radius of 3, right? Now there's a cylinder, yeah? And what's the radius?
2.
What axis is it running along?
Z.
There's a cylinder cutting through this thing. And its radius is 2. So the object I actually want to find the volume of. Oh wait, let's see. So what did it say? I want it inside the parabola, but outside the cylinder, right? So which region am I actually describing?
Between 2 and 3.
Between 2 and 3, right? So it's actually the outside that I care about. Right? Out here. So again, this is another place where reading the question is going to be very important. When they tell you inside this or outside that or above this or below that, they're actually telling you where. It could also be in here, and they could have described that as something like inside the cylinder, below the surface, above the XY plane. You can describe it like that. Or the region inside both the cylinder and the paraboloid above the XY plane. They can describe it in various ways, but you should actually always know where they're talking about. So I want it inside the paraboloid, but outside the cylinder. So I'm looking on the outside. So if I were to draw my region D in the XY plane, what would it look like?
A circle inside of a circle.
That's the region D. Now if I had to describe D, R and theta, how would I describe it? R goes from?
No, from 2 to 3.
2 to 3.
And theta goes from 0 to 2 pi.
Okay. Now the volume would look like pi, 2 to 3. What would I integrate? Top minus bottom, right? What's the top function?
9 minus x squared minus y.
The parabola, which is 9 minus r squared. And the bottom function?
That would be r squared.
No, it's still 0.
Why is it still 0? X squared plus y squared equals 4.
That's describing the region. Right? If you look at the bottom part of the surface.
I see.
Like, if you think of someone standing inside this solid.
Yeah.
Like, if you stand on the floor, z equals 0, the roof would be the parabola. Right? So that would be the top, the bottom would be z equals 0.
And then you get the other parameters inside that.
So it's sort of the same that we had before.
We know that the bottom is the XY plane. Otherwise, it's going to just go down at the bottom.
Yeah, I have to say that. They'd have to say that, because otherwise it could go down forever. You're right. So we've actually done this before, so it's just going to be 2 pi times 9 over 2 r squared minus r to the 4 over 4 to 10 over 3. This is 81 over 2 minus 81 over 4 minus 18 minus 42 here. So this is 2 pi times 81 over 4 minus 14. 14 is what over 4? 56 over 4. So this just becomes this over 2, that over 2. So it's just what? 81 minus 56 is what?
25.
Huh?
25. 24. Yeah, 24.
What? How do you just skip to a step? Like you skip to
Oh, that was I'm using the thing where we said if you have f of x times g of y dx dy, you can literally just split them off. I'm using that. So here my function of theta is just a constant, which means I can sort of factor it out. Yeah, I can plug in theta separately and just multiply them. One last problem. Okay, how do we do this one?
We're doing C now?
C, yes. C's get degrees.
Yes, I agree with that.
Draw the region, right? It'll give you ideas how to set it up.
Okay, so again, that's the upside down parabola.
This one's an upside down paraboloid.
And the other one's a cylinder, but it doesn't give us a radius.
So this goes down like that. and it starts at 8, right?
Right.
This is what?
That's another problem.
That's another parabola.
Oh.
But that one
It's
opens
not
up.
C-squared. Right, right.
How do I find the region D? You have to intersect them, right? It's going to intersect at a certain point. And that intersection I'm going to project down. It's going to look sort of circular. That's how I'm going to find my D. How do I figure out where they intersect?
Symmetrical.
So here I have for intersection, I have 8 minus x squared minus y squared equals x squared plus y squared. Right? So this means 4 is equal to x squared plus y squared. Right? So this is actually x squared plus y squared equals 4, which actually tells me my region. This would mean r goes between 0 and 2. Theta goes between 0 and 2 pi. And so I can, so what would the volume look like?
Would we want to do this top to bottom or bottom to top?
It's a volume.
or-
It's always like a top
Left to
minus
right.
bottom. So what's
Does
the?
it 0 is less than r or theta is less than r?
0 is less than.
No, this is 0. This is 0. Right? It's this circle. Because we want to find the volume of this thing. So the volume is what here? Huh? So if you're a little man trapped inside this solid, what's the top and what's the bottom? The top would be this surface here, right? The bottom would be this one here. So the top is the 8 minus x squared minus y squared, which I can write as 8 minus r squared. That's the top. Minus the bottom, which is just x squared plus y squared, which is r squared.
In this case, does it matter which way you do it?
What do you mean?
If you do the top minus the bottom,
Yes, it matters. The bottom minus the top would give you a negative volume, right? So here, this would look like, well again, there are no thetas inside here, so I can evaluate the thetas separately. I can just put that 2 pi here, and then worry about this guy. So that's 0 to 2 of 8r, this is minus 2r squared, so this is 8r minus 2r cubed. So this would be 4r squared minus 1/2 r to the 4th. 2 here, I would put 4 times 4 is 16, 2 here, 16 is 8. So that's just going to be 8 times 2. That's pretty much polar coordinates. The homework is going to give you a lot more practice in a lot of different situations. So we'll stop there. So 12.2 and 12.3 tomorrow.